Kinetics. So we have looked at reactions in terms of what mass proportion or mole proportion I need in order to get the amount of product that I want to make. We've talked about it thermodynamically in terms of the energy cost and how easily something will have to occur, under what conditions they might need to occur, high temperature or low temperature. So now we're going to be looking at it in terms of kinetics. In other words, how much of my product I can expect to make given how the reaction moves. And so this oftentimes requires us to have an understanding of something that goes to equilibrium, which will be next. So we have to remind ourselves that most reactions are usually multi-step, and that for an effective reaction to occur, because it's a matter of collisions occurring, those collisions have to have both the correct orientation and enough energy. So again, the handshake analogy, if we're acting as reactants where we're about to shake hands, we have to meet in the correct orientation. I have to be face to face with the person. We have to be slightly offset so that my right hand meets their right hand. And it has to be with enough energy. If we kind of meet where just our fingertips touch, we're not going to have an actual handshake. So in general, the rate of a reaction increases as temperature increases. And the explanation for that would be that as my temperature increases, the velocity of my molecules increase. Therefore, the number of collisions that I have increase per time. And so things are just going to be moving more rapidly. It's not that my reactions become more effective. Everything's just happening at a faster rate. And so that's why I'm seeing more of my reaction occurring. If I were to graph a reaction, the rate of a reaction as a function of time, most reactions will follow this kind of curve. It will start out very quickly, and then it will start to taper off. And where this taper off depends on whether the reaction goes to completion or not. And this is because it's a concentration dependence, right? So if I need to collide, the reactants need to collide, the more concentrated something is, the more opportunities there are to have the collisions that will have correct orientation and enough energy. So I use dodgeball as my analogy. So in gym class, if you're in PE and you're playing dodgeball, the rate of the reaction at first is going to be very quick. Many people are going to be getting out very rapidly at the beginning because the number of participants in the dodgeball game is going to be so concentrated that it's going to be easy to hit your target. As the dodgeball game progresses, it becomes harder and harder for a person to get out because they're spaced farther apart, because it's usually the people who are just hanging out and not wanting to participate and are too timid to run to get to the ball in order to get somebody out. And so at this point, the game just gets interminable, right? And so you can see from that an analogy of how the rate of reaction as you go through time starts to peter out until it finally becomes really hard to get that last person out. We can measure the rate of a reaction either by the disappearance of the reactant, right? So the negative concentration of my reactant over time, or the appearance of my product, the positive appearance of the concentration increase of my product over time. And honestly, it's whatever's easier to track, right? So if I'm creating a gas, like in our magnesium hydrochloric acid lab, it's easier to measure how much volume of gas I'm creating rather than trying to figure out how much magnesium I'm losing. If my reactant is a colored solution and it becomes colorless, it'll be easy to track that rate of disappearance of that color so that I can no longer see that color solution. We could use generation of heat, right? So if it's an exothermic or endothermic reaction, we can track the temperature change over time, and that's also showing the rate of the reaction. So whatever is easier for us to track, remember that chemistry is always a lab-based science, and so we're going to be using what we're able to do in the lab. So part of what we look at, especially knowing that these are multi-step reactions, is what effect does changing the concentration of a reactant have on the overall rate of reaction? And that's called the rate order. So think about it, it's sandwich making, because you might think that just simply increasing any reactant will increase the rate of the reaction. Let's say that I have 4 steps to my reaction. The first reaction is the person slicing the bread. The second reaction is where the person layers on the meat. The third person spreads the mustard on the top one, and the fourth person wraps the sandwich in aluminum foil. Well, it turns out that station number 2, layering on the meat, takes the longest because you're having an array of meats that you want to add on to it, and there's a specific order that you're supposed to do this. So layering on the meat is our rate determining step. It takes the longest. If I add more people to slice bread or to spread mustard, it's not going to help. I'm not going to see my product rate increase. Right? So simply increasing the concentration of any of these reactants is not necessarily going to change the rate of the reaction. This is something that can't be figured out simply by looking at the equation. It must be determined experimentally, or as we say in science, on inspection. So when we actually look at the data, so part of what we do is we double the concentration of just one of the reactants, and we observe that effect on the overall rate. If doubling the concentration has no effect, the rate is multiplied by 1, that rate order is 0 because I take my doubling and to the 0 power, it's that power that's going to be our rate order. If doubling the concentration doubles the rate, multiplies it by 2, then that's a rate order of 1. Whatever I do to the reactant, the same thing happens to my rate order. If it has an exponential effect, right, if I double it and the rate is multiplied by 4, that's a rate order of 2, and so on and so forth. You know, if I multiply by 2 and the rate order increases by 16, that would be fourth order. If the rate order is cut in half, which can happen, you can actually slow down the rate of the reaction, then that would be a rate order of negative 1/2, negative 1, not 1/2, let me correct that, because that would be 2 to the negative 1 power. You can have rate orders that are non-whole numbers as well. So again, just so this double and 2 doesn't mess you up, if I triple the concentration, nothing happens, 0 order. If I triple the concentration and the rate also triples, that's first order. If I triple the concentration and it's multiplied by 9, that's second order. If I triple the concentration and the rate is cut into 1/3 of the amount, then that would be a negative 1 order. Rate orders can be positive, negative, 0, or even fractions of an order. When you look at all the reactants together, the overall rate order is the sum of the rate orders of each of the reactants. So here's an example. I'm looking at this reaction of nitrogen monoxide and oxygen, creating nitrogen dioxide. And I have 3 trials. I have 2 trials in which I'm doubling the concentration of nitrogen monoxide, but keeping the concentration of oxygen the same. So here I've doubled this, and I see my rate of my reaction has increased by 4. That means my rate order for NO is second order. When I look at the green, here I've doubled my oxygen concentration, but my nitrogen monoxide concentration remains the same. And what has happened is that I've doubled my rate of my reaction. So what I've done to this happens to this. So the rate order with respect to oxygen is 1. My overall rate order then would be 3 because I add my 2 rate orders. The rate orders become superscripts around concentration, and my overall rate order is going to be the addition of the 2 superscripts. So my rate is actually equal to K times the concentration of my reactants to their order power. Right? So if NO is to the second order, that would be to the second power. Oxygen is to the first order, so it would be to the first power. And the K actually makes these 2 equal, not just proportional. The K is specific to the conditions, and so I would find the K by substitution. I would take one of my lines, and so in this case I took my first line, where my rate was equal to 0.014, and then I'm multiplying K times 0.1 to the second power times 0.250. And I get 0.16, and the units are dependent on the rate order.